Okay, so we are looking at statistics in the binomial theorem. Now, when you get a question like this in the exam, you don't necessarily know if it's a binomial theorem or whether it's geometric or normal distribution. So we have to first analyze the question and then decide what it's going to fall into. So Fiona uses a calculator to produce 12 random integers between 7 and 21 exclusively. So let's just write out, because there's not too many numbers there. So let's write them out. So 15, 16, 17, 18, 19, 20, 21. So inclusive means it includes those numbers. So that's inclusive. We include 7 and 1. So when you see inclusive here, it must include the 7 and 21. Then it says the random variable x is the number of these integers, of these 12 integers, which are multiples of 5. Okay, so what we can do is we can actually circle the multiples of 5, like that. So we know that 3 out of these numbers are 5. So we've got 3. Now let's look at how many numbers we had. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. There were 15 numbers, right? So n was equal to 15. And so the variable is the number of those 15 that are multiples of 5. Well, so it's 3 out of those 15. So when you say, well, okay, we're going to pick those numbers, and what are the chances of a multiple of 5? So it's either going to be successful and you pick a multiple of 5, or unsuccessful and you pick one of the other numbers like 7 or 8. So it's binomial because it means you've either got a success or a failure. So success is picking a 5 or a 10 or 15 or 20. Unsuccessful is the picking of a non-multiple of 5. So, you know, we could say that our P is equal to probability of success is 0.15, right? As 3 divided by 15. If you put that in a calculator, you get 0.2, which means our Q, which is our not successful, must be 1 minus that. 1 minus 0.2, which is 0.8. Because your P and Q must always add up to 1, because probabilities add up to 1. So we've got our 15 numbers, 3 out of 15 is our success. And then we can, it's producing 12 random integers. So it's producing, so actually our N is actually 12. Sorry, our N is 12. Because it's producing 12 random integers. So it's actually, that's where it can be a bit confusing, because the number of integers, 15, is not how many you choose. That's just the number of possibilities. So there's 15 possibilities, but I'm choosing 12 of them. I'm producing 12. So producing, as what we're saying is we're choosing 12, right? And so now we've kind of analyzed the question. We've got enough information there that hopefully we can answer pretty much anything. So the first question says, what's the, state the distribution, right? So that's the distribution will be the N, which is 12, and the probability of success, which is 0.2. Okay, so when you put the distribution in, you put your X, and then it's how many do you choose? So it's your N and your 12. So let's just write down what we should say for the formula. So that would be the N and then the success, right? So when they want that sample, in fact, we missed out something here. I missed out something here. We need to say what kind of distribution it is. because the parameters of the distribution, you say what kind as well. So it's binary, binomial distribution. So let's just put bin there. Okay. So, okay, so the type of distribution. Okay, so let's just put that formula so that we can. So I'm putting in this formula so you can answer any type of these questions. So we'll put in blue, no, not blue. I haven't used orange. So orange, this is the type here. So this could either be binomial or it could be geometric, or it could be normal. Okay, so we'll look at each three of these. I'll put some links to videos and I'll do one of each type so that you can see the different types. Now then, the probability of success, 0.2 there, over here. So first, after that was the number. So this is how many you choose. And then the probability of success goes here. Okay, so this is in. So this is like the number of tests you do, or number of results, or how many times you perform the test. So here we're producing 12 numbers. So we're testing it 12 times. And then the success rate is next. So that would be the answer for the first one in green, light green there. Okay, so now that we've got the parameters, it says calculate the probability that it would be between 3 and 5. Okay, so we know it's binomial theorem. So when we do probability between 3 and 5, we're going to do first the probability. So, well, let's see. So that x is between 3 and 5. So the parameters. Okay, so x equals. So the first one would be, well, when they say 3 and 5, they don't mean pick a number 3 or 5, because obviously there's no number. It's 3 or 5 out of those 12. What is probability? 3 out of the 12 that you choose are multiples of 5. Okay. So in other words, what we're saying is, where x is equal to 3 first. So this would be the chance that you picked exactly 3 multiples of 5. So let's just look at what that might look like. So say you picked an 8, a 9, then a 16. It's generating them randomly, and you're doing it 12 times. 13, another 8, because you can pick the same one twice. What we've got 1, 2, it's 4. Let's take another 7, 20, 19. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So what it just said, the computer calculator generated these 12 numbers. And so when we looked at it later, we would go, okay, well, there were 2 multiples of 5 here. So there are so many different ways that you could generate these different numbers. Well, you could have, it's almost impossible, but you could have produced 20 12 times. No, but it's unlikely. It's going to produce, just random numbers. And we are looking for, well, how often would it produce exactly 3 multiples of 5? So example, if this 16 had been a 15, that would have been one of our options, which would have produced 3 multiples of 5. Okay, so the way we work that out is using the binomial theorem, where we say, well, how many are we choosing? Well, first of all, how many tests are there? So how many times are we running this test? And we're running it 12 times. Okay, so we do the n is 12, right? 12. But then how many times we're looking for when we 12 choose 3, right? So this would be 3 multiples of 5. Let's just put that in over there. 12 choose 3. And then a probability of success. So these would be all the successful ones. Well, how many successful ones are we looking for? We're looking for 3 successes, right? 3 multiples of 5. 3 numbers that are multiples of 5. So that's the success. Well, let's actually just let's change the 16 to a 15. Because I think it'll be easier to now explain. So if we put this as a 15 here, then this would be an example where we did have 3 multiples of 5. So look, we've got 3 successes, 1, 2, 3. So that would be times, so you times the 3 successes, right? And the first one is 0.2. And the next one is 0.2. And the next one is 0.2. So remember, when you want to work out probabilities and the independent events, which it's true because your first number does not depend on what you picked before. It's random every time. So the independent 0.2 times 0.2 times 0.2, those are your successful. But of course, you've also got to account for the unsuccessful 9 of them, right? 1, 2. So in a sense, it'd be 0.8 times 0.8 times 0.8 times 0.8. So if you were to kind of do this together, you would times everything by 0.8, all the unsuccessfuls, times 0.8 times 0.2. So if I was to do it for this specific one, like you would say 0.8 times 0.8, and this would be all multiplied together. But the binomial theorem does it, it makes it much simpler by just saying, well, do the successes and then do the failures. And of course, 0.2 times 0.2 is 0.2 to the 3, and 0.8 9 times is just 0.8 to the power of 9. Now, you have a calculator that can do this. So if you get out your calculator, put this button in, find out what that is, and then times that by 0.2 to the 3, and times 0.8 to the 9. Now, for those of you who don't have this button, or if you're just interested in what this means, what it means is that it's 12 factorial over, now this is 12 times 11, so 12 factorial with this exclamation mark means 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 1. And then what you do is you take the 3 factorial at the bottom, so 3 times 1 times 3 times 2 times 1. And then you say 12 minus 3 is 9. And then it's the 9 factorial times 9 factorial. So you could also put that into your calculator, put the factorial button. You could even do some of the work by, you could even times it out and then cancel some of the things. But that is what this 12 combination 3 means, is this. Okay, so that's the 3. Now the 4, now that I've explained the 3, I'm not going to do the whole 4, the whole explanation. We're just going to say, well, it'll be 12 combination, and instead of a 3, we've got 4 successes. And so then our successes is times 0.2 to the 4 and times 0.8 to the 8, because there would then be 8 unsuccessful. Times those together. And then final one is our 5. Next, 5. Okay, and then if you're following on nicely in your head, you're going, I know what's happening. He's going to put not a 4, he's going to put a 5. If you're not thinking that, then means you're not following. You'll have to watch the video again, which is fine. Just watch it until you understand it. And then what do I put for my unsuccessfuls? I will then have, if I've got 5 successes, 7 unsuccessful. Okay. And so this 12 combination 4, that part of it would have been 12 factorial over, let's just see, over 4 factorial times 8 factorial equals. Okay, now once you've got this, so you're going to say 12 factorial over 3 factorial times 9 factorial times 0.2 to the 3 times 0.8 to the 9. That's going to give you an answer. So let me just stop having to spend time changing colors. The colors is just for explanation point of view. So this would be times 0.2 factor 3 times 0.8 to the 9 times 0.2 to the 4 times 0.8 times 0.2 to the 5 times 0.8 to the 7. Okay, and those are going to give us the probability of choosing exactly 3, the probability of choosing exactly 4, and the probability of choosing exactly 5, multiples of 5 out of the 12 that we choose. And then what we do is the probability of all of that being either 3, 4, 5 is when we just add those probabilities together. Okay. So, okay, so if you put that in your calculator, you should get 0.23622, 0.13287, 0.05315. Add those up and you get a probability of 0.422. So just under 5. Okay, so now that we've done that question, let's look at question 3, which is probably going to be, they usually get slightly harder, although not always. So this is find the least possible value of n that none of the integers is a multiple of 5. Okay, none of the integers is a multiple of 5. So if none of the integers is a multiple of 5, so that would then be, let's have a look. So this 15 would not be an integer of 5 anymore. So say this was like an 8 as well, and this 20 was a 6, and this 20 was a 3. So then this 0.2 now would actually be, the probability of an 8 would now be actually the unsuccessfuls, which is 0.8, and this being a 0.8, not a 0.2, and 0.8. So we're looking basically at nothing being successful, because if there are no integers of 5, none of the integers is a multiple of 5. We're looking at all the failures. So rather than work out the successes, let's just look at the failures. So what's the probability of them being 12 failures? Well, that would just be 0.8 times 0.8 12 times, right? So it'll just be probability would equal so well, let's do it. So we'll say x equals 0, let's say. there's no successes, equals. And I'm going to use the binomial theorem notation, even though I kind of don't need to, just to explain how it works, even with stuff like this. So we take 12 and we choose 0. So remember that then it was our successes. So we are still going to put our successes in as 0.2. But you're going to say 0 here. It's a 0 because there's no successes. And then that's all failures. Just to prove that you still use this formula, even though often you're in the memo and stuff, they won't even put the 0.2. They'll just put 0.8 to the 12. Don't worry about that. We are going to be a bit more mathematically correct and put the 12 in and show, and the 0, and show how this stuff, these two things actually end up being 1. So this 12 choose 0 ends up being 12 factorial over, and then the 0 factorial, well, 0 factorial is actually just 1. It's not 0, by the way, because then you'd have undefined. And then 12 minus 0 is 12. So we'd have 12 factorial. So do you see that the 12s end up canceling? The 0 is factorial is just 1. And so that's just 1. Anything to the power of 0 is 1. And so that's also 1. And so we end up with just 1 times 1. And that's why often the memo won't even show these. And then it'll say 0.8 to the 12. Okay. Oh, but we're not choosing 12. So this is interesting. So that would be if we were choosing 12. But this question actually asks, when is the probability less than 0? So actually, we don't know that this is 12. We just know that there'll be no successes. So this was more just an explanation. This isn't answering the question. So the question says, when would we get a probability of 0.01 or less? And so then what we put in is our 0.08 here. Sorry, 0.8, the unsuccessfuls, to the power of, well, how many times would it be that this would be? Well, let's put this 0.8 to the 12, Liam, in the calculator. What's 0.8 to the 12 equal to? 0.8 to the power of 12. What would that probability be?
0.0687.
0.0687. So we see that if to the 12, it wouldn't have a probability of less than 0. It would have a probability of 0.06. So not a probability of less than 0.01. So we know we would have to pick more. We'd have to choose more. So we'd have to make this number bigger. So more 0.8s to make this probability 0.01 or less. So let's just find out how many we would need for the probability to be 0.01, right? And then whatever that number is, we would then either round up or just make it 1 bigger, because it's got to be less than 0.01. So how many times would we have to do this to make the probability 0.01? So for the 0.08 to the 12, we'd have to do to the n now. Now we use logs, right? So log base 0.8, the number by itself 0.01. And what do we get? Okay. So have you got that button in your calculator? There should be a log, this button, where you put a 0.8 and a 0.01, or you could just do your log laws. You could just say log 0.01 over log 0.8. That would also work. Either way, so you've got either this button. What do you get for this? If you got the button there, Liam.
I have, but it's giving me an error.
Okay, so are you putting in, is it the silver calculator?
Yes.
Okay, so are you using, I think the button is near the on, I think it's just below the on button, it's around there, and I think it's shift. It should look like this. This is the button here.
Okay, I figured it out. It's 20.6377.
20.637. Okay, so that sounds right. So 20.637, if you put log 001. So if you don't have a nice calculator that has this button in pink, you can just use log 0.01 over log 0.8. You get 20.637. Now this, we can't have, you can't choose 20.637 times. Now, if you round down to 20, that would be a probability of greater than 0.01. So we need to round up. So even if it had been 20.02, which is close to 20, we still have to round up. You're always going to round up because the rounding down takes the probability above 0.01. So our n is equal to 21. Okay, so that's that question, binomial theorem, and that's the type of one you're going to get in the exam. As I said, I'm going to put a link to the different types of distributions, the binomial, the geometric, and the normal, so that you can just know the difference between them. But hopefully the binomial theorem, if you've looked at the video on binomial theorems, which I'll also post a link to, then this question, if you understand this question, you understand a lot about the binomial theorem. If you don't still understand, then subscribe and watch some more videos.